Okay. And I guess I'll just go ahead and introduce you. So hi, everyone. Super excited to have Dylan Losey today here. He's an assistant professor in mechanical engineering at Virginia Tech. His research interests lie at the intersection of human-robot interaction, learning, and control. Specifically, he develops algorithms that enable robots to personalize their behavior for human collaborators. Dylan was previously a postdoc scholar at Stanford University. He earned his doctoral degree in mechanical engineering from Rice University in 2018, and his bachelor's degree in mechanical engineering from Vanderbilt University in 2014. And he actually was at UC Berkeley as well. He interned in Anka's group in summer before his fourth year, actually. Dylan has also received Best Paper Awards from the Coral Conference and the Transactions on Mechatronics. And today, Dylan's going to talk about robots that learn to influence humans. And we're actually also going to see some preview of two papers that are going to be presented at ICRA in a couple months. So that's super exciting. Thank you, Dylan, for joining us. I know that it's super late there. Very much appreciated. Take it away.
Thank you very much for the kind introduction, and thank you everyone for having me. So I'm Dylan. I'm a professor at Virginia Tech, and I want to talk about some of the work that my group's been doing on how robots can learn to influence humans. So let's get started. Okay, so I've got a couple of videos just to kind of ground this talk and some applications I'm thinking about. This first one, pretty self-explanatory, self-driving car. Of course, this car needs to be used sensors, cameras, capture the world around it, make good decisions, but it also needs to think about pedestrians, people on the road, the drivers within this car. It needs to think about the humans that it's working with and that it's working for. Maybe a closer connection between a human and a robot. This is a video of a Da Vinci surgical robotic system. Here we're going to have a doctor or surgeon who is remotely controlling that robot as it moves around inside the person's body. He's got something that kind of looks like a joystick, like a little pincer device that he's holding. He's got a camera so he can see what's going on. And he's teleoperating this robot as it moves around to try to perform this minimally invasive surgery. So here, of course, we have like a very, very close connection between the human and robot, not only for the doctor, but also this robot operating within this human's body. This final example, this is my favorite. So this is a person with a long-term physical disability. They are controlling a robot arm, a wheelchair-mounted robot arm using their hand. So this particular gentleman has got some use of his right arm, and he's using that to operate a joystick, press buttons, to move this arm around to do really basic everyday tasks, grabbing something from the fridge. Here he's opening a door. And so he's trying to control this robot to do things just around the house. So in all three of these videos, one thing that strikes me and that I think is pretty important to highlight is that really there's a bidirectional information exchange here. Of course, the robot is gathering information. It is learning from the person that it's working with. But at the same time, that person or the people who are working with that robot are also gathering information from that autonomous system. They're seeing how it behaves, its tendencies, its patterns. And so both sides, both the human and robot, are learning something from this interaction. So to kind of visualize this, I've got a human, I've got a robot. We have this human-robot interaction going on. At the start of the interaction, like both of us are kind of a black box. We don't know what each other are thinking. We've got these squiggly lines in each other's heads. What I want to do, and this is a long-term goal, what I want to do with human-robot interaction is I want to make sure that we harness that interaction to spark mutual understanding. So that I, as the human, I understand what my robot is thinking, what it's doing, and the robot, on the flip side, it understands, oh, this is what Dylan wants. This is how I can help this specific user. So I want to make sure that both sides get on the same page. We both have this mutual understanding through human-robot interaction. So today I want to highlight some of the work that my group has been doing. I'm at Virginia Tech. My group is called CoLab, and I put a link to the website here if you'd like to learn more. I'll bring this up again at the end of the talk. So going back to our diagram, we've got human-robot interaction. The first part that I want to talk about is transferring that expertise from the human to the robot. I want that robot to get a good understanding of the human that they're working with or the human they're working for. Of course, this is suggestive of some type of robot learning, and there are many different ways the robots can build this mental model of their human partners. So I'm going to highlight one that is particularly near and dear to me, and that is how robots can, specifically assistive robots, can interpret human inputs. So I'm going to have two videos here with roughly the same scenario as what we had before. We've got a gentleman who's operating this wheelchair-mounted robot arm. He's using it to do basic tasks. On the right, just a high-level reaching task for, it looks like a baking soda. And on the left, a more precise manipulation, moving this wheelchair-mounted robot arm around to stab oranges. You might imagine if you were to own or to have one of these robot arms, what you might need to do to control the different inputs you might need to provide, the level of precision that you might need in order to do these tasks. On the left of this slide, I've got a picture of one of these commercial devices, this Canova wheelchair-mounted robot arm, and kind of within the state of the art, the way that they're controlled is through direct end effector teleoperation. And what I mean by that is you have your joystick, typically it's 1 or 2 degrees of freedom. Let's just say it's 2 degrees of freedom. So you can press up, down, left, right. In one mode, that's going to map to a plane, like the robot moving in, let's say, the XY plane. You press a button, you switch to another mode. Now that up, down, left, right maps the robot moving in the Z-axis, maybe rotating around that Z-axis. And then finally, you press another button, and now you're controlling the 2 other angles, maybe the roll and the pitch of this robot arm. And so you have 6 degrees of freedom for your end effector, you have 2 degrees of freedom for your joystick, and so you're pressing buttons to switch between to map from those 2 degrees of freedom up to the 6 degrees of freedom of the robot arm. And this is, a very effective baseline way that people are in practice controlling these robot arms right now. And I've listed a few works that use this particular teleoperation scheme in practice. But if you go back to this video of the gentleman using this end effector scheme, you'll notice he keeps slapping the side or pressing on the side of this. That's the press of the button to switch between these different modes. It's hard to figure out what mode he wants to be in. And hopefully this video illustrates just how challenging it is to manually control the robot through every single part of this task. Of course, we're robotics experts. We want to figure out how we can help introduce autonomy, make this problem a little bit easier so the person doesn't have to do everything for themselves. The robot recognizes, oh, like you want to open the fridge, let me help you automate that task. So one way that we can learn to assist humans in this scenario, or learn to inject some type of autonomy, is by learning a mapping. And what I mean by that mapping is, I'm going to provide a nonlinear mapping from your joystick inputs to the robot actions. And I want to make sure that the actions I get out of this are going to be assistive within your current context. So if you're in front of the fridge and you press right on the joystick, perhaps the robot should move and open the fridge. In this case, I've got a robot arm next to a table. One axis moves the arm across the table. The other one does a type of pouring motion. So I want to map your inputs to these more complicated motions. So I've done some prior work on this. As I said, this has been like kind of a long-term project. And within this prior work, the robot learns these mappings directly from human demonstrations. So here I am physically moving this robot arm around to try to show it, hey, I want you to move across the table and I want you to pour. I guess a question for the audience, with our target population in mind, can you think of any problems with collecting these demonstrations physically? Does that pose any challenges?
Can I just speak?
Yeah, please jump in.
I mean, it's super difficult physically to do that. And even if you can do it, it's going to result in extremely noisy demonstrations.
Yeah, so physically, it might be hard to find the demonstrations themselves. And maybe going one step beyond that, the population that we're working with for these assistive robot arms, generally, they're not going to be able to physically stand up and actually provide the demonstrations, right? Like they are using this wheelchair-mounted robot arm in the first place. And so collecting these demonstrations either through a physical or, as we will see, a teleoperation input, it's not necessarily going to be the best way to go about this. And so the work I want to highlight is going to try to move away from this and learn these mappings in a different way. Before I get into the new work, I want to briefly overview this specific method that we've been using so far. Here, we collect a data set of demonstrations. So, for example, these physical demonstrations I'm showing right here. That includes the actions I provide, these high-dimensional actions, as well as the context in which I provide them. For example, in this, it's the state and the robot's belief over the task. The reason I need the context is because I might need to take different actions in different contexts. When I'm right in front of the fridge, maybe opening the fridge door makes sense. But when I'm next to a cup of coffee, opening that door doesn't make any sense. Now, picking up the cup or pouring the cup are reasonable actions to take. So I'm going to take my data set, these state action pairs. I'm going to embed it down to some latent space. The dimension of that latent space is going to be the same as the dimensions of my joystick. Then I'm going to harness a decoder to go from that latent space, as well as the context that I'm currently in, to some high dimensional actions. The idea being that now, I as the user, I'm going to have my joystick. This joystick is directly mapping to the latent actions. When I press down, that is this latent action Z. The robot decodes that to a high-level reconstructed action, such as moving across the table or forward. So it's a conditional autoencoder sort of framework that we're using to learn this nonlinear mapping from joystick inputs to robot actions. And as I highlighted so far, we've been learning this directly on a set of demonstrations that the human either physically provides or they provide by teleoperating the robot. But in our recent work, what we tried to do is learn these mappings, learn these assistive strategies without any type of human supervision. And this is work that's going to be at ICRA, I guess, next month, coming up soon. We've got kind of a four-step process for this. It's not particularly complicated. And I just want to briefly highlight the overall process that we came up with. The first step is an offline. The robot is going to learn a policy that maximizes state entropy. I don't think there's any specific method that you need to use here. I listed two particular papers that we found helpful on this slide, but any type of RL approach that is somewhat reward agnostic, that searches for diverse skills or behaviors would be appropriate in this scenario. The one that we stuck with has a buffer of states. It tries to cluster those states into K different clusters. And then whenever it sees a new state, it rewards this robot if it finds a new state that is very different from any of the clusters that it has seen recently. Basically encourages the robot to continually look for new states within the world, new contexts. So if you look at the image on the left with this robot messing around with a drawer, I can get new states by pulling this drawer farther open, pushing it farther closed, maybe knocking this whole thing off the table. All of those would introduce new states the robot has not seen. Whereas just jittering around in space isn't really going to introduce any new states because I'm not messing around with the environment. So first, we're going to learn this policy that maximizes state entropy. Once we have that policy, then we're going to roll that out. And now these rollouts are going to form our demonstrations. Previously, the person was physically providing those demonstrations. Now we're rolling out this policy to get the demonstrations. Finally, we're going to use the exact same approach I described earlier, this autoencoder approach, to learn latent actions from the demonstrations. Once we have that, then we can just hook up the joystick. The user takes that joystick, they're now pressing it up, down, left, right, and the robot maps that to these more complicated actions. For example, here this user is trying to open the drawer halfway. Well, the robot has learned actions that will close the drawer, that will open the drawer. Now by using your latent actions, you're able to map your joystick inputs to the robot now doing this task. So to kind of give you a sense of how this works, we try to compare this unsupervised latent action approach to what we've done before, latent actions trained either using human physical demonstrations, like me kinesthetically guiding the robot, or teleoperated demonstrations where I'm just using a joystick to show the robot the different tasks. Here are the results from the kinesthetic demonstrations. These are when I'm physically showing the robot the motions. I've got 4 different tasks: pouring, opening, scooping, and pushing. And the plots, you'll see the final state error, the difference between where the robot was supposed to end up and where it actually ended up. Here, we asked, I think, 10 different users to provide the demonstrations. And then we had a simulated human actually control the robot to do these different tasks. The simulated human used some type of Boltzmann rational model to select actions and move through the space. So here's our initial error. Here's the error with teleoperation. We also tried introducing a bit of noise into this teleoperation just to see what might actually happen in practice if we have a user that perhaps has some spasticity in their inputs, so they don't always press exactly how they want it. And as you might expect, introducing more noise into those teleoperation inputs causes higher final state error. And then finally, we've tried this approach that learns essentially without demonstrations. It learns through this offline reinforcement learning. And here you'll find it overall, in general, we find a lower error with this approach, with the simulated humans. We then tried comparing this unsupervised approach to an industry standard. Here, we're talking about direct and effective teleoperation, which, like I mentioned before, you have these different modes. You're pressing buttons, up, down, left, right. Here's some videos from the user study. On the left is this end effector, sort of the industry standard approach. On the right, we're using this approach that learns to decode your inputs, but does not have any demonstrations that you have provided when it learns this mapping. The task is kind of a mess. It's like moving things around, got a jumble of stuff in the kitchen, trying to pick things up and pour them. Intuitively, the reason that this is easier is because things like pouring, instead of you having to press multiple different buttons to control the orientation of the robot, now like one single direction, like, oh, I'm now above this object. When I press to the right, the robot knows that that maps to a pouring task. For this particular user, I cut their time roughly in half using this approach. So I think the results were good. I wouldn't say they were fully conclusive. I think that it very much depends, and there's some nuances here on how you train this reinforcement learning approach. Like, what knowledge do you have about the environment? How much time do you have to train it? How accurate is your simulated environment to the real environment? I think those are all still questions that need to be answered. But at least in this proof of concept study, we can see that without any actual demonstrations from the user, we're still able to learn mappings that make it easier for them to do tasks on a daily basis. But one question that comes to mind, I often get this question, I think about it myself a lot, is when you're messing around with one of these joysticks, pressing these different directions, or whatever the case may be, what do those mean semantically? Like, if I am pressing the joystick, for example, to the right, I've mentioned before, oh, pressing right means I want to pour this, or pressing right means I want to open the fridge. But like, how do I as a user know that without some type of experience with the system? Like, how do I get that knowledge in the first place? Sure, you could just tell the person, well, you'll figure it out over time. But I would like some system that's more intuitive, that's more practical to the human. And so the second work I want to highlight deals with this problem. How do we map these inputs to robot actions? And really what I'm thinking about here is this mapping between the inputs you provide on the joystick and what the robot learns from these inputs. So here, I've got a user who is pressing left and right. Left is supposed to be for this can of soup, and right is for the notepad. But there's no reason it has to be left and right for this soup and notepad. I mean, you could foreseeably just pick up, that should be the soup, and down, that's notepad, or any other combination. There's no reason it has to be this. So our insight or our recognition is that this is actually a convention, right? We've got some intuitive convention that for us, it's natural that left and right should be soup and notepad, but any choice is feasible. Because there are many valid conventions, the robot can pick one of them, but it's not obvious to me as the user which of these conventions are what I might want to use. Going back to our previous example, is pressing right pouring? Is pressing right opening the fridge? Like, those both sound reasonable to me. I don't know which one the robot wants. How can I figure out that convention from this robotic system? So our idea, also at ICRA this year, is that robots can reveal these conventions by showing communicative inputs. Again, I think there are many ways that robots can reveal information. This is just one way they can reveal their information. And here I want to reveal by showing, reveal by the robot actually taking these actions to try to show the human, hey, this is a better way for you to control me, to indicate what it looks like you're trying to indicate right now. So the setup is fairly simple. I don't have too much math in this talk. I think this is one of the only slides where I have any equations. So here, the robot first tries to take a stab at what it thinks the human is trying to do. It figures out, okay, my guess is this theta star. That's the task that I think you want me to do. I'm going to spit out this action AR. That is the action that best communicates the task that I think you want. In this case, I've got the soup, I've got this notepad, and I spit out this action going directly up. Because according to my, i.e. the robot's convention, going up is the most communicative action you can take. But there's a trade-off, right? If you only ever take these communicative actions, you might never accomplish the task. Like, you might end up always going up and never actually reaching for the soup. And so we take a constrained optimization approach where the robot is optimizing for these communicative actions while constraining the quality of these actions to make sure that it is efficient within some epsilon bound of performance. So here, the robot is ensured that it's moving roughly towards this can of soup on the right side of your screen. Here's kind of a video just sort of shows what happens in practice. At first, the human is trying to operate this robot towards the can of soup. The robot or the notepad, whichever the case may be, the robot tries to figure out what task it is, and then it exaggerates its own motion, moving farther to the left or farther to the right, trying to show the person, hey, if you want the can of soup or if you want the notepad, this is a way that you could convey this to me. Of course, like, it doesn't always have to be this left-right convention. We tried putting these cans of soups and notepads in different places. And every time the robot's just trying to indicate to the person, this, based on how I infer and based on how I learn from your inputs, this is the best way for you to teach me what task you want me to do. Our goal was to see whether humans could sort of internalize or take this input and extend it to other scenarios. Like if I've seen a robot to help me exaggerate a few cases, why then transfer this so that I myself am taking these exaggerated inputs and conveying my intent to the robot more quickly and concisely. So here's one picture from the user study where the person is again trying to transfer this convention to a new scenario. We also tried more complicated tasks, although not shown in this video. On the right, you'll see there's a drawer, and we actually tried different conventions that a human could use to indicate, hey, I want you to open the drawer. And these were like non-intuitive, like sinusoidal conventions to tell the robot that I wanted to do this drawer task. Overall, I think, again, we had success with this. We compared it to two options. One is like the robot does nothing, and you just need to figure this out through experience. That's shown in lighter gray. In darker gray is written, and what we did here is we crowdsourced some written explanations of these conventions. So we showed videos on Amazon Mechanical Turk to a variety of different users, and they wrote in descriptions of what they thought, like how they would describe it to someone. And then we gave these written descriptions to participants in our user study. At first, like we expected this written description to do really, really well. The reason it did not perform as well as our approach is because often like writing a sentence in words like about how the robot should move is not as clear as actually watching the robot itself move. When you see it move, you're like, oh, okay, this is kind of how it should be. But when it's written, like how far is right? Like what does left really mean in this context? Those words become a little bit ambiguous, whereas actually seeing it puts it in context. I think it made it more clear to our participants what the robot really wanted. So this project is mostly about how the robot can use its actions to try to convey to the person the conventions that it uses for these joystick inputs. Okay, so those two together kind of wrap up just one idea on how we can transfer this expertise from the human to the robot, so the robot builds some type of mental model of the human that's working with. And that's one side of human-robot interaction, right? One side of human-robot interaction is robots that learn from humans. But the other side, at least for me, is how humans can learn from robots. I want to take that expertise of whatever that robot is learning and transfer it back to the human. The idea being that without this knowledge, the human can't have this seamless collaboration with the system. They don't know what to expect. They don't know what the robot's thinking. Everything kind of breaks down without this feedback loop. And so this next part of the talk, I want to focus on how humans can get a sense of what the robot is learning. So we've tried a few different things here. Here I'm just highlighting two previous projects that we did last year on this topic. On the left, we've got an active learning framework where the robot is trying to ask questions to the human. It's asking these questions to learn as quickly as possible. So it's trying to maximize information gain as it chooses these questions. However, we're also trading this off with another objective where the robot tries to ask questions that communicate what it has learned and what it is still confused about. The idea being that we don't want the robot to ask questions that mislead the person into thinking the robot is totally confused and does not understand the task at all. If you'd like to learn more, I'd recommend Sohail's paper, Here's What I've Learned, Asking Questions That Reveal Reward Learning, kind of a tongue twister. On the right, this is another video. This is actually part of a senior design project that spun off into this journal paper, where we have two different feedback modalities. One is on the person's wrist. It's kind of small, but hopefully you can see it. There's a white wristband. This is actually a set of motors, a set of vibratactors that will buzz and notify the person of whenever the robot's confused. And then, of course, they're wearing this augmented reality. They're wearing a HoloLens 1. When they look towards the robot visualizes different trajectories in space. And these visualizations let the person know what the robot is confused about. So a combination of haptics to let you know when, and then augmented reality to let you know what. So this one is communicating inferred goals with passive augmented reality and active haptic feedback. Okay, so that's in the past. These are two that we've tried. I want to talk about something new. So what I noticed so far, especially when we're dealing with the questions, the active learning paper, is there seemed to be a fundamental trade-off between the robot gaining information from the person and the robot revealing information from the person. I'm just showing one equation that we used in that paper, which really encodes this trade-off. On the left, in orange, this is the robot trying to choose questions to gain information, whereas on the right, in yellow, the robot is trying to choose questions that show what is learned to the person. This is just one example of a problem that we've seen in many different papers. On the bottom, I've taken an image from Generating Legible Motion by Drogan and Srinivasa. In this particular paper, the robot is trying to indicate to the person which of these two bottles it wants to pick up. It wants to pick up the one on the right, and you'll notice that if you keep increasing like this idea of revealing information, it moves farther and farther off to the right. But this is a less and less efficient motion. So if we were trying to use the robot's motions themselves to communicate information to the human, we have a bit of a dilemma. On the one hand, we want to make sure that these motions actually do the task correctly, right? We want to reach for that bottle. We want to ask informative questions. But on the other hand, we want to reveal things to the person, right? We want to exaggerate. We want to try to show the person what we're learning. This kind of overloads a single modality, right? We're using just this motion, and now we're trying to use it for two different things. We are faced with a trade-off where sometimes we're going to have to sacrifice one or the other. So with that sort of background in mind, we thought of how can we create a new channel completely separate from robot motion that will communicate the robot's learning back to the person. We're calling this, the name is still a little unclear. We called this a haptic display, but I think people didn't like that. We also thought about calling this haptic skin, but I personally find that creepy. So name unsure, but this is a haptic display that is wrapped around the robot's arm. This was at RoboSoft last week. And this is joint work, I should mention joint work with Purdue University and Laura Blumenschmidt. So we're gonna wrap this haptic array around the robot arm. Here I've got some videos of the students actually making this array to kind of give you a sense of what actually is going on here. This is also because, although it doesn't look like it, I am a mechanical engineering professor. So whenever we actually build something, I have to highlight it, I have to show it off, just because it's so rare in my work that I actually build or make anything. So here we're marking these tubes, marking patterns into this plastic. We're then going to heat seal this plastic into arrays, like little square-like arrays. We're going to cut out just a connector, and this is going to be a pneumatic system. So we're going to be pushing air into and out of the system. When we push air in, it's going to inflate. When I pull air out, it's going to deflate. And we're going to control the pressure within this 1 degree of freedom array. Let me skip to the next slide. Yep. Finally, we're going to tape a bunch of these together to make this sleeve, kind of like a sleeve, like an arm sleeve. And then we're going to put this sleeve on the robot. In this case, they put it on, this is at Purdue University. They put it on one of these like PVC pipe, and then just to kind of show what it looks like when you inflate it and deflate it. So here's at 1 PSI. This is its inflation, person feeling it. Here's at 3 PSI. We found that roughly between 1 and 3 PSI is something that people can discern. Like one of the major questions we had was like, will people actually be able to tell the difference, or is this totally binary? Like, is it just off or on and that's all people can notice? Or can you be like, hey, this is 2.5 PSI. Do you notice the difference between that and 2 PSI? One thing that we found when testing for just noticeable differences is people were able to tell within a resolution of about 0.5 PSI. So we can, although it's not continuous, we can provide a variety of different signals with a single degree of freedom here. Okay, so once we got the band, we did some user studies. So here we've got 3 different methods that we tried in this user study. On the left, we've got a GUI. You might notice this is Sagar, he's controlling the robot arm. And you notice the screen in the background that's showing like a percentage. That's the robot's uncertainty as a percentage. When I'm saying uncertainty here, what I mean is we did like Dagger. We did ensemble Dagger. So we trained Dagger on a variety of different networks. We compare all those different networks. We check out the actions that each network outputs. And then we look at essentially the variation across those outputs. If they all output the same thing, the robot knows what to do, it's confident. If they output different things, the robot is confused, it's uncertain, and that's when the uncertainty will rise. So we've scaled that between 0 and 100 on this GUI. In the middle, flat, this is that same haptic array just flat on the table. And then on the far right, this is our proposed system. Again, it's like kind of like a linear mapping where 1 PSI means the robot is like fully confident, knows what it's doing. 3 PSI, that's when the robot's like, I have no clue, can you help me out? So the idea for the experiment was people would physically guide the robot throughout the entire test. So here it's like closing one drawer, pulling open another drawer, that's the task. The whole time they're getting feedback, whether it's from the GUI, the flat, or the wrap system. They try to figure out where in this task is the robot confused. They go back to that area where it was confused, and then they're just going to show only that section of the task again. The idea being that, like, sure, our ultimate goal is for the robot to learn the task, but by providing this feedback, we actually close the loop and make it easier for you to teach the robot, because now you know where it's confused and where it actually knows what it's doing. So here you can show it just the part where it's confused about when you're trying to teach this robot. Okay, so here are some videos from the user study. You'll notice this particular user keeps looking up at the screen. The reason why is because there's the GUI is right behind the camera here. And so they're looking at that GUI to see, like, is the robot confused? Is it confident? Here for the flat, they keep their hand off the robot to feel this flat display. This one was by far the worst because people generally needed 2 arms to control the robot. So anytime you had to take one off, that was not going to be helpful. Then here is the wrap display. I think the reason this is effective is because people can the whole time they can focus on teaching the task. Like they don't need to divert their gaze. They don't need to take their hand off of it. The whole time they can just focus on the task, and underneath their hands, they feel this feedback. Another exciting thing about this feedback, or something that motivates it to me, is whenever you ask people to wear a device, like wear a haptic wristband or wear augmented reality, like you saw in the previous slides, that's a burden, right? That's something that I'm gonna have to wear whenever I want to use the system. The nice thing about this is now it's mounted on the robot. So it's not something that I have to wear, it's something that the robot is wearing instead. And hopefully that makes it a little bit more easy and convenient for people to use. Okay, so here's another user with a shelving task. One additional task, same general framework, and you'll notice again in these videos, the person keeps taking their eyes up to look at the screen or using their hand to check this flat display. So let me skip to this next slide. This is some bloopers. One thing that we noticed a lot was that people would often completely forget to check things, like they would not look at the GUI or they would not touch the flat display. And so they wouldn't realize when the robot was confident or when it was confused. I think this, again, supports my claim that perhaps it's better to have this on the robot itself so you don't have to remember, oh, do I need to look here? Do I need to check this thing? Like it's already there. When you're touching the robot, you're already feeling this under your hands. Okay, so the results generally supported this wrapped display. Like I said, wrapped was the best, the GUI was probably the second best, and this flat was the worst of the three. People were able to teach the robot a little bit more efficiently. What I mean by that is with the same amount of or less time, people were able to teach the robot what they wanted more accurately. And they also subjectively preferred this to the alternatives. One concern that I had, and that Laura had, was when people were feeling this under their hands, they might find it, I don't know, somehow displeasing that like this thing could move under their hands as they're trying to teach the robot, somehow annoying. And so we wanted to check and see subjectively, like, is this okay? Like, does this wrap display bother you in any way when you're trying to teach the robot? In general, people were fine with it. They didn't find it annoying or bothersome. Okay, so this is our most recent work on how robots can convey information back to humans. I mentioned a few different things. I mentioned questions. I talked about augmented reality and haptics, and finally the haptic display. I think all those modalities are exciting. I don't think any modality is better than the others. I think the final solution will be some combination of all these different feedback modalities. But in some way, I want to open up that black box. Right? I want to show to the person what that robot is thinking to make it easier for that person to then interact and collaborate with the robot on a daily basis. So the final thing, the final part of this talk is kind of trying to put everything together. So right, I've got the robot that's learning from the human that now understands what the robot's thinking. With those two things, I actually think we can do better than either by themselves. I think we can get new and emergent behaviors through this human-robot interaction when both agents are reasoning about and responding to one another. So the final part of this talk, I want to go from bidirectional information exchanges from human to robot, now towards influential and emergent behaviors. And this is some previous work that we've done on this, and I'll lead into new work. So this previous work, we had two robots, no human yet, just two robots, that were playing air hockey. The robot on the right is programmed with some heuristics, and it knows exactly how to play air hockey. Like it's not learning anything. We've told it exactly what to do. The robot on your left, that's just blocking the puck, that robot has, at the beginning of training, like no clue what even air hockey is. All it knows is like, I get +1 reward if I block the puck, -1 if I miss it. What makes this challenging is the agent on the right switches how they shoot the puck based on how the agent on the left blocks. And so you can't just learn a stationary policy that's going to work well. You have to be able to model, predict, and respond to the partner you're working with. So this work was published in Coral 2020. There's been some follow-up work at Coral 2021. But one common trait within this existing work is that although it does learn to influence partners, for example, the robot, it doesn't really work if you switch that robot out and now put in a person. So here I am. We took out that robot, and now I'm trying to play air hockey. And I've actually practiced quite a bit to make these shots so that my partner can block them. Because I have to, when I shoot this puck, I have to shoot it the exact same direction and speed and with the exact same rules as the robot did when they were training together, right? This robot is only trained with one robot partner. Now, if a human comes in and I play totally differently, the robot has no clue how to play air hockey anymore. Like I'm breaking the rules that it thought it learned, it doesn't know what to do. So one constraint for this existing work is that although it does learn to influence, it relies on humans always behaving the exact same way. So, and this is some recent work by Sagar and Sohail. We wanted to see if we can develop robots that learn to robust policies that can influence changing human partners. So we switched up the game a little bit. Now we're not going to do air hockey. We're going to try to build a tower. But the difference is now we want to actually work with humans. And we recognize that we might not always be working with the same people, right? Different people might come along, different people might want to play with this robot. So we need to figure out a way we can all work together. This is called RILI, R-I-L-I, robustly influencing latent intent. Okay, so the way it's, and again, not too much math, but just a little framework. The way it works is we start off with a pool of changing partners. And these are partners I get access to at training time. So I can spend as much time with these partners as I want. This could be partners that are programmed into some simulated world, whatever the case may be. So for these simulated partners or pre-programmed partners that I'm working with, I'm going to learn a dynamic model. I'm going to play with them. I'm going to learn essentially through an encoder-decoder structure. I'm going to learn a latent space that models that partner, that tells me how they change over time, what their dynamics are, how to anticipate what they're going to do. I'm also going to learn a policy that is conditioned on these latent dynamics that lets me know how to play with that partner. And because I'm seeing multiple partners at training time, I'm learning how to work with each of these different partners. Our approach does not assume that we know like the identity of the current partner, even if a partner switches. We never see any of that. We just keep seeing the input-output, like states actions from these interactions. We have to figure out who the partner is and how to play with them as we go along. So that's all fine and good, right? We're learning how to work with multiple humans. But of course, we're not going to only see those humans, right? And of course, at test time, we're going to come across new humans. Then we also need to figure out how do we coordinate. And one of the key challenges here, and something that I often face in my research, is just the limitations of data, right? When I work with a human, I'm only going to get them in the lab for, I don't know, 30 minutes, 45 minutes. I don't have a ton of time to work with that human. And so whatever system we come up with, it's got to be able to adapt pretty quickly. It's got to have some type of rapid adaptation to new partners. What helps us is that although humans are unique, although we each have our own patterns or behaviors, there are some common traits. Like we do have some existing, I don't know, there are connections between different humans. So although I might build a tower different from you, perhaps you build a tower similar to your friend or something along those lines. And so the robot can take what it's learned from one partner and transfer some of it to work with a new partner. And that's what's going to happen in this second part of our approach, where the robot, it again, tries to learn an autoencoder that maps from the dynamics, that essentially learns the dynamics of the new partner. But then instead of trying to learn an entirely new policy, which would not be feasible just with the time that we have with this particular user, what I'm going to do is I'm going to take my existing policy that I've learned with my training set of users, and I'm trying to see, are there any behaviors from that current policy that I have that could still work with this new user? I mean, maybe there are none. Maybe I have to learn totally new things. But before I do that, is there anything that I already know that could work with these new users? And so we end up doing something like model predictive control, where we sample a bunch of different policies a bunch of different trajectories that we've seen before. We try to figure out, do any of these make sense given my prediction of the current user? If so, let me try using one of those when I'm working with this new partner. So I tried this in a variety of different environments: a circle environment, a driving environment, like kind of like a Carla environment, and a robot environment. I just want to show the videos from the user study, although we have more extensive simulation results in those different worlds. So here, again, it's a robot trying to help a person build a tower. We've got an asymmetry of information. Only the robot knows the correct tower to build. It's this purple, green, red, yellow tower. The person has no clue what the right tower is, but the robot learns how they take these blocks and assemble them. Most people would take the closest block and put it on the top or the bottom. And so the robot is trying to move these blocks in a way so that, oh, I'll take this block, put it closer to you. I'll take this other block, pull it farther away from you, so that you build the tower that I want. On the left, we're using Silly, one of the existing methods, which works well in some scenarios, but doesn't work well here. It just puts all the blocks together in a blob. And the person just is like, whatever, there's a blob of blocks, I'll just take whatever and make some tower. So it ends up pretty random. Let me start that video one more time. On the right, we've got the this RILI approach, where the robot is spacing these blocks out in such a way that the person's like, all right, sure, I'll just take this closest one and put it here, or I'll take the farthest one and put it here. As long as the person is reasonably consistent, the robot is able to space these blocks out in a way that works with that partner and increases our reward over time. One final thing I want to highlight here is the number of interactions you'll see on the bottom. This is from up 1 to 35 interactions. I will admit that building a tower is not crazy hard. However, learning how to influence people to build a tower is relatively challenging, and we're excited that we're able to do this in one sitting in like 30 to 50 interactions. Here are 35 interactions. Okay, so this is like learning these different emergent and influential behaviors that hopefully kind of connect everything together. So that now the human knows what the robot's doing, the robot knows what the human's doing, and the robot can go one step farther to influence the human towards behaviors that are going to coordinate well with that robotic system. So a couple final thoughts. I guess my main takeaway from this last year of research has been not something that's necessarily new, perhaps it's a truism, but something worth thinking about, is that whenever a robot takes actions or whenever your autonomous system takes actions near humans, those actions can be influential, right? They can cause the person to think about, hey, what is this robot thinking? What is it doing? What might it do in the future? When I see that robot moving around, I try to reason about what it could be thinking of doing. And so that's something that we shouldn't ignore, right? We definitely want to harness that so that the human knows, all right, based on these actions, I should be doing this. Or based on these robot actions, I should avoid the robot. Like, it has no clue what's going on. We need to make sure that we harness this potential for robots to influence humans in a way that coordinates both agents together so we both understand what's going on and we can both coordinate and both solve these tasks. So with that thought, I'd like to thank my students, Shonak, Sagar, Sohail, and Anath. And I'd be happy to take any questions. This is my final slide. If you are interested in more of these works or any of the publications, please follow this link. We've got our works listed there. So thank you.
Awesome, thank you, Dylan. Yeah, I guess we have another 10 minutes or so for questions. I guess I can start off with a very small one. I noticed, I think in your what was it called, wrapped user study, I noticed that the one thing that the one measure that didn't have a significant result was natural. And I guess I'm just curious, what does it mean to be natural in that problem setting anyway?
Yeah, this is a good question. So this goes back to my just neurotic nature and my worry that when people felt this, they were gonna be like, this feels creepy or weird. I don't like this thing growing under my hand. And so that question was about like, does this bother you that this thing is like inflating or deflating under your hand? People were totally fine with it. I was just worried, so we asked that question.
I see. So in this case, well, in this case, you didn't want to see statistical significance.
I think they were all like, people thought all of them were fine. Like the GUI, flat, wrap, like none of them were more or less natural than the others, I guess was our conclusion.
Yep, sounds good.
I actually have two questions.
Hey,
Depending
Jared.
on time. Hey, Dylan, great talk. Thanks.
Yeah.
I have a question about the first work you mentioned about learning without human demonstration.
Yes.
What I got from the presentation is I was super impressed by the quality of the robot policies, especially as you mentioned that they're learned in unsupervised way. But if you look at the trajectories, it's actually able to like lift cups very stably or open drawers. And those are super impressive. And I can think of like different ways of doing it, but I don't think those ways will do as well. For instance, you could use end effector control, but I don't feel like those would still give as high the trajectories as the ones you showed. So I was wondering, do you have like a special way of structuring the action space such that these are so high quality? Or yeah, basically what's the secret to get so good unsupervised trajectories?
Yeah, that's a really good question. So the secret sauce, we were pretty excited about this paper called Pebble, which you might be familiar with from Peter Beal's group. Although we did not use their approach for like asking questions, the way that they harnessed like the unsupervised reinforcement learning or learning these skills through self-exploration reinforcement, I'm blanking on the word, but the way that they set that up was really helpful to us. So we did something similar where we did that clustering. We had a buffer of states. We clustered those different states and we tried to see if this new state is similar or different to the states we've seen before. One thing I should mention that probably is part of the secret sauce is what is a state, right? Like, how do you define state? Is it an image? In this case, no. It is the position of the robot arm, like the joint position, perhaps the position of the end effector. I can't remember that one exactly, but at least the position of the robot arm, probably the position of the end effector and its orientation, as well as some information about the world that I'm working in, right? If I don't know where the drawer is, then I have no like sense of whether or not I'm moving around or interacting with it. If I don't know how far the drawer is open, then I don't know that I'm actually introducing more variability into the state by opening that drawer. So you have to define the state in such a way that like these actions now are somehow increasing my entropy, or they're different, or they're new from the robot's perspective. So the assumption we made is that we have a simulated version of the world, like we have the simulated drawer in my PyBullet simulation, and I can directly measure the position of that drawer. I can directly measure the position of all the drawers. Like I can sense these different things. Moving forward, you probably want to use a camera there. And that's, I think, would introduce another big challenge, because everything we're working on so far is relatively low dimensional states, like less than 20. But once you have a camera, everything blows up. So I don't know like whether or not that's something you've already been thinking about, but that certainly would make the problem a lot harder than what we were looking at.
Cool. Thanks.
Yeah, of course.
I guess I'll just go with my second question here now. I was quite impressed by the last work you presented on influencing human and the pipeline. From what I understand, you train with a pool of simulated humans, and then at test time you identify and find the closest simulated humans and use model predictive control. And I've been thinking about this similar problem too, but one thing that I'm a little bit not sure what to best do is at test time, you're almost solving two questions. I feel like one is you want to maximize the information and identify that human as fast as possible, and only if you identify that human well can you do the downstream of rolling out your best performing policies and whatnot. But if you want to optimize for identification, then you're almost solving a different objective. So it's almost like a two-step approach. And in the work that I've seen and in the work you presented, that it's not done that way. Is that correct? And basically, I was wondering what's your thought on this?
Yeah, let me clarify a little bit on our approach. I think your description's accurate. I just want to add a few other words to it. So our approach has got two parts, and this is very similar to Lily, the original paper on this, where you've got an autoencoder that's learning to basically represent or model all the partners. And then you've got a policy that takes in whatever that autoencoder has for latent space, uses that to predict like what action should I take right now. So we're still keeping those two parts. We're changing the autoencoder a bit. Previously, like we had a fully connected like multi-layer perceptron type of autoencoder. Now we have a GRU autoencoder, so we can capture, instead of just the dynamics of one partner, we can capture multiple different partner dynamics. That's a small change, but practically useful. On the right side, for the policy, in the Lily paper, we always have that same policy. We train with it, play with it. That's the same thing the whole time. Now what we're going to do in this Lily approach is we train the policy, like you said, on these practice users for as long as we want. Right? We've got a decently good working policy. Then I'm going to sample from that policy a set of behaviors. Again, I could cluster them into some different types of trajectories. I could just randomly sample 100 times, like here are 100 different behaviors I've learned. But I'm going to take a bunch of these different behaviors that I've learned, and I'm going to treat that as like, these are the behaviors that I can do with my new human, right? Like this, I'm constraining myself just to these X behaviors that I've sampled. I'm updating the autoencoder for the new person, right? I'm still training to figure out how do I work with this new partner, but I'm not learning the policy at all. All I'm doing is the autoencoder spits out, hey, like this is a latent variable. I take my decoder, I take my, these different trajectory rollouts. I say, hey, for this latent variable and for this trajectory decoder, what do you think I'm going to get for reward? So we are still like adapting and learning about the new partner just through this autoencoder, but we're not changing the policy, because from our point of view, like the policy, or at least from our results, training the policy took much longer than training the autoencoder. The autoencoder is quite quick. The policy takes a while to learn. Even if you were to like pause and like resume training, it is still quite slow. And in the paper, you can see more of that, like more side-by-side comparisons. So to your point though, about like, I think this actually ties to something I mentioned earlier in the talk, where like you're overloading a single information source. You're completely right. Like if I want to optimize for gathering information and solving this task, those are two completely different objectives, right? So if I want to optimize for gathering information, I might do the task in a really terrible way just so the person shows me something else so I can learn it more quickly. This is like something that's of course solved by like things like Palm DPs, right? Because they know like, okay, this is how I trade off between, explore, exploit, whatever. But we don't use those, right? And we also don't know what the right trade-off is between explore and exploit. In our case, I think we've broken it into two parts. The autoencoder is only exploring, the policy is only exploiting, if that like analogy still holds or convinces you.
Sounds good. Yeah.
Awesome.
Awesome. Well, the hour is up, so unless anyone else has any more questions, then I think we can just wrap it up. I'm sure that people can probably email you too with more questions if necessary.